All right. Welcome. This is the Unit 7 test review, and I am just going to walk through all of it. I'm just going to start from number one and go through everything. I won't explain incredibly in depth, but I'll explain some. If you want the really detailed explanations, I'd go rewatch some of those lesson videos. But hopefully, this will be enough. If you got any questions about the test review or want to refine anything, hopefully this will address that. So let's just get started. All right. So I split this test review into 3 parts. Part 1 is, do you know the basics? So we got to know the basics to be successful on the exam. And long term, going into pre-calc, going into calculus, this is really what matters. If we don't got everything after this, well, that can get fine-tuned down the line. But what's really important is that we know the basics going forward, okay? So, first question here is a true or false statements. So let's just talk about these. So first one says, if the point 3, 8 lies on the graph of f, then the point -8, comma, -3 must be on the graph of f inverse. Well, we can't say that might be true, right? But that's not true based on the fact because of 3, 8, right? Given only this information, I cannot conclude that that is true, all right? So I will say that this is not always true, so this statement is false. It could be true, and I didn't do a true, false, or sometimes true, whatever. The reason being, 3, 8 does not tell us that -8, -3 is on the graph. You see, when we look at the inverse of a point xy, the inverse of that becomes yx. So, if I have the point 3, 8, the inverse of that point, the point that would be guaranteed to be on the graph of f inverse, would be 8, 3. I do not put negative signs here. I simply swap the x and y. Okay. If the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is the nth root of a times b. True. Yes, this is true. This is the basic fact that I can say, hey, we've done this before, right? Like the square root of 6 equals the square root of 2 times 3, which equals the square root of 2 times the square root of 3. We've been using this property since Algebra 1, so yeah, because you do some simplifying radicals in Algebra 1. Sorry, I'm just rewriting that 6. Yeah, that's true. If the nth root of a and the nth root of b are real numbers, then if I add those roots, then that's the equivalent of taking the nth root of their sum being a and b. That is not true. Pretty much never. I think the only time that might be true is when a and b are 0. And maybe some combination of 0 and another number. But aside from that, I don't think so. Okay? For example, if let's say I got the square root of 1 plus the square root of 2, which equals, how about this? Let's just do square root of 1 plus square root of 4 equals square root of 5, question mark, is that true? Well, square root of 1 is 1, and square root of 4 is 2, so that's 1 plus 3 equals 5? No, that's not true, so that's false. Okay, all right. For any real numbers a and b, and any positive integer n, if a to the nth power equals b, then b is an nth root of a. And you want to be careful with this because a lot of the language here is good, but it's really this last then statement. then b is an nth root of a. No, false. This should say a is an nth root of b. Right, because if you, or hold on, wait. If a equals b, then b is the nth root of a. Yeah. Sorry. This is equivalent to saying a to the nth root of b. Yeah. I gotta double check on that later. I'm pretty sure. Yeah, it's the a versus the b. It's the placement of, is a an nth root of b, or is b an nth root of a? Yeah. Yeah, b's not an nth root of a. Sorry, yeah, see, yeah, you got to think about this, right? That's the language. This should say that a is an nth root of b, because you see, this quite literally says a equals the nth root of b. And when we say equals, we use the word is. Sorry, I was starting to confuse myself. I just want to be sure. I didn't want to give the wrong statement in the video. Okay, so false. All right. Now, if the nth root of a and the nth root of b are real numbers and b is not 0, then the nth root of a over the nth root of b is equal to the nth root of a over b. True. This is one of our facts. Okay, it's just one of our properties. It's same reason multiplication is true. Yeah? Okay. The conjugate of 2 root 3 plus root 10 is 2 root 3 minus root 10. Also true. Yeah, that's how I define conjugates. Yeah? A plus bi, the conjugates are a minus bi. Now, I'm using imaginary numbers here, but whatever, right? The idea of conjugate is, yeah, just switching that sign. Okay, expression of x to the power of negative 3, y to the power of negative 2 is equivalent to y squared over yx cubed. Yes, this is true. And this is true because y to the negative 2 equals 1 over y squared, and x to the negative 3 equals 1 over x to the 3. So that means 1 over x to the negative 3 equals x to the 3. Yeah? So you essentially just swap their places, and that is true. One goes on top, the other one goes on bottom. Okay, last one. If the nth root of a is a real number and m is an integer, then a to the power of m over n is the mth root of a to the n. Oh, that's backwards. False. It should be the nth root of a to the m. Yeah? So this one is false. Be careful with that. Where that n goes, where that m goes. Now that's super important, right? Because if I say square root of a, let's say a cubed, that's going to be a to the 3/2. That is not going to be a to the 2/3. Okay? We have to have that correct placement of m and n. Okay, there's the true or false statements. Let's move on. Number 2, the graph of the function g of x equals negative 3 over 2 times root x minus 3 plus 8 given below. And it asks what is the domain and range of g, which is the graph, and what is the domain and range of g inverse. Okay, well, the domain of g, we're going to give this an interval notation. Here is x equals 3, and it looks like it extends on out to forever towards infinity. And here is y at 8, so I say 8, and that extends downwards towards negative infinity. So we'll say that the domain of x, of g, which is the x values, bracket starts at 3 and continues towards infinity. However, the range of g is going to be from negative infinity up to 8. Real quick, I want to remember, because one of the common mistakes I saw on our quiz in this unit was writing these intervals backwards. So do not write infinity, well, especially not infinity bracket to 3. Okay, don't do that. So I might say right here, do not write bracket 8 to negative infinity. Yeah? It has to be least to smallest. Or, sorry, least to greatest. What? Can't think. I actually just woke up from a nap, by the way. Least, greatest. Left to right, okay? Got to have that consistency there. It's about our notation. It has to be consistent. Now that I've identified the domain and range of G, I know that the domain and range of G inverse is just swapping those. You see, the domain of G is the range of G inverse. So my range is 3 to infinity. And my domain is negative infinity to 8. This is because you're swapping all your x and y values, right? Every single one of those is mirrored. So naturally, if the domain was a set of x values and you mirror that over to the y values, then that's your new range. Okay. Number 3. A lot of little ones here. Rewrite each expression in radical form using rational exponents. So when I say rational exponents, that means fractional exponents. That's what I mean by that. Or that is what is meant by that. Not just me, just math in general. So if I have the nth root of a to the m, that is a to the m over n. Okay, and we're going to use that fact here. So this, option A, that's the square root of x to the 1. Therefore, this is x to the 1/2. By using this rule right here. Okay. Moving on to B. The m is your power of 7. Your root is 4, so it's b to the power of 7/4. Messed up that 4. Boop. And then C, the exponent is on the outside, but you see, remember that for our rule here, I can say that this is also equal to the nth root of a to the m, which is true. All right, that is true. So this is y to the 5/3. If you have a question as to why that is true, I might ask you, can you prove it? Can you prove it using properties of exponents? Yes. But if you'll want to come talk to me about that so we can work on that together, that'd be cool. But you don't have to. Only if you're curious. Option D, cube root of C. Well, that's the cube root of c to the first power, so this is naturally c to the 1/3. Now, option E, I've got 1 over the square root of n cubed. Now, see, we're going to write this as 1 over n to the 3/2. But remember our other rule, right? Let's say 1 over x to the negative n. That's going to go up in the numerator, like so. Which means this actually equals n to the negative 3/2. So I'll put that into the negative 3/2. Done. Okay? And this is just using rational exponents. Part of me says you probably could just leave it as 1 over 3 3 halves into the power of 3 halves, but I think the idea here was just to recognize that it's negative. Now, F, we're going to use our rules of exponents here, like so. So this is fourth root of 2p cubed. Now, you got to be careful here. Notice that p is the thing getting cubed. So I might write this as, well, we don't want to put the 3 on the 2, do we? So let's put it on the outside. Or, no, I can't do that, can I? See, my concern is it's not 2p quantity cubed, it's 2p cubed. P is the only thing being cubed in that expression. So you can't write this as 2p to the 3/4. You can't do that. No. So we have to fiddle with this a little bit. Let's try. Well, okay. Here's what we could do. We could say, leave the cube in there. Let's say that this is 2p cubed to the power of 1/4. And that this is getting squared, right? So what I've done is I've rewritten the fourth root as power of 1/4. I'll use properties of exponents when I raise a power to a power. This is the power rule for exponents. I'll leave my 2p cubed alone, but the 1/4 to the power of 2, that's going to be 1/4 times 2. So I'll say this is 2p cubed to the half. And then I like to use the word distribute, but it's not the distributive property, which so I should be careful with my language there. There's a rule that when you have something like that, right? If you have a to the n times b to the n, this equals ab to the n. Yeah? So you can essentially apply this power to these other guys here. So I've got 2 to the 1/2 times p cubed to the 1/2. That's essentially what I've done. I've applied the power to both terms. And now I've got 2 to the half p to the 3/2. So if I only used fractional exponents, this would be 2 to the 1/2 p to the 3/2. Yes, if I'm only using fractional exponents. You gotta be careful there, because it's not 2p quantity cubed. Okay? All right. That one was a little tricky. Hopefully you got that. Let's move on. Number 4, simplify radicals. Okay. And be sure to use absolute value signs when necessary. Okay. So a lot of this, simplifying radicals, we just use the rational exponents idea. And when the absolute value signs part, well, this happens when, I'm going to write it, when you take an even root of, I don't know, something, and I get blah, blah, blah to an odd power, then use absolute value bars like this. Okay? Or, well, the power goes inside the absolute value bars like that. Okay? That is the only time I need them. I don't need them for odd roots at all, and I don't need them for even roots when the result has an even power. Because if it has an even power in the result, then it's going to get rid of the negative either way. So, Okay, so start with a, r to the 8. So under a square root, so I can say this is r to the 8 halves, which is just r to the 4th. Done. And look, if you understand this fact, you really should just be able to jump from here to here. You don't have to rewrite it, but that's the logic behind it. That's the reason why we get this. Y to the 14 over 2, well, that's y to the 7. But hey, that matches that rule I was just talking about. So it should be absolute value y to the 7th, because I've taken an even root of y to the 14th, and the result had an odd power, so to put the absolute value there. Letter C. Oh, thankfully, cube root of 216 is nice. That's just -6. And then it's 15 over 3, so it's n to the 5. Yeah? That's how you should be hopefully getting to the point of evaluating these. But you could write this as cube root of -216 times n to the 15 over 3. And of course, cube root of -216 is -6, and 15 over 3, yes, 5. Okay. Here, this is x to the 30 over 6, which we know is x to the power of 5. And again, the root was even. The index was even, so I got to put those absolute value bars there. Letter E, I've got a very simple, simplify the 12 as root 4 times 3, so that's 2 root 3. As for x, well, root x to the 7th. I'm going to split this up. So I'll say x to the 7 halves. And then I'll split this up as x to the 6 halves plus 1 half. Because we're simplifying, right? So this is now x to the 6 halves times x to the half. I'm just using rule of exponents here, which is now x cubed times x to the 1 half. I am taking an even root, so I should probably include the absolute value bars there. Yeah? And so my result, this is x cubed times square root x, if you're putting it back into the radical. Because I don't need rational. Yeah, I'm just rewriting it. Okay. So 2 root 3 and, okay, so it's 2 absolute value x cubed and times square root. What goes in the root is 3 and x. Nice. Next one is cube root of 16 and m to the 8th. So we'll say cube root of 16, that's cube root of 8 times 2. So the cube root of 8 is 2, cube root 2. And then cube root of m to the 8, well, that's m to the 8 thirds. I can't make this any smaller. 8 thirds. And so I, again, think of it like this. What's your remainder, right? If you're doing 8 divided by 3, right? How many times does 3 evenly divide into that? Because if you get 3 over 3, you get 1. If you get 6 over 3, you get 2. If you get 9 over 3, you get 3. So those are powers you could take out of the radical now and just put on the outside. Because if I had the cube root of x to the 6, well, that's just x to the 6 thirds, so that's x squared. And so I could just pull it out like that. So what I'm going to do is I know that 6 is divisible by 3, and that's the closest number. Well, not the closest, 9 is, but I don't want to use subtraction. So m to the 6 thirds plus 2 thirds, which of course is m to the 6 thirds times m to the 2 thirds. So that is m squared and the cube root of m squared. Aha. So this should say 2m squared on the outside times the cube root of And the things going inside there is 2m squared. Ha-ha! 2m squared, 2m squared. But one's on the outside, one's on the inside. Cool. Beautiful. Look at that. How wonderful. Man, how long is this video going to be? Sheesh. Oh, we've got all this stuff to go. Yikes. Maybe I'll split these into a 3-parter. Okay. All right, number 5. Write the equivalent expression in radical form. Simplify if possible. Well, I just use the same rule that I've been using over and over again. X to the 1 over n is the nth root of x. Done. 1 over x to the half, well, that is, you could say that that's equal to x to the negative 1/2, right? Or, you could say 1 over root x, and yeah, and that's all I really want to do. Yeah, because I don't want to do, say, root x to the negative 1. That's silly. You could say 1 over root x. Or, if you rationalize the denominator, you could say that this is root x over x. And you can get the rationalize the denominator by doing times root x over root x, which is root x over x. I'm actually fine here whether or not you leave it as 1 over root x or root x over x. I just want you to recognize what the equivalent radical is, okay? I don't really care about like going all the way and rationalize the denominator on this problem. Okay, so this one, option C, t to the negative 1 tells you it goes in the bottom. So it's really going to be t to the 5/2 in the bottom. So it's like 1 over, the denominator is 2, so it's a square root of t to the 5th. Okay, so you could write that. 1 over square root t to the 5th. Except that's probably what I meant by simplify, because you can pull some stuff out. So 1 over t to the power of 5. So let's actually do that. This will be equivalent to 1 over t squared root t. Okay, so if you want to make that your answer, you can say 1 over t squared root t. Okay. And you say, how did you get that, Mr. Spake? T to the 5 is t to the 4 plus 1. So if this is 5/2, 4/2, 1/2, right? Then it's t squared times t to the 1/2, which is your t squared root t. That's what I'm doing there, okay? Kind of the similar idea of what we were doing up there. Now, if I want to rationalize the denominator, I could do times root t over root t to get root t over t cubed. So I could say that. Or root t over t cubed. If I rationalize the denominator, okay? Which it's fine if you don't on these problems. I didn't really ask that. Okay. Do it again. So 1 over q to the negative 2, that equals just q squared to the 2/3. Which, if you now use the rule of multiplying your exponents, this is q to the 4/3, which means this is the cube root of q to the 4th. Well, but let's simplify, right? That's q to the 3/3 plus 1/3. So it's equal q to the 1 times q to the 1/3, which means it is q times the cube root. Oh, isn't that funny? Oh, what a letter, right? The cube root. right? Get it? The I'm going to do it. The cube root. I say, haha. Okay, I'll stop. Yeah, the cube root of q. Okay. All right. Okay, number 6. Here's the rationalized denominator practice. Man, all of this is in red. Red, 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 red. Maybe I'll start doing the work in blue and then put the answer in red. Yeah, I like that. I'm going to start doing that. Okay. Times, to rationalize the denominator, when you have just a radical in the bottom, you simply multiply by that radical on top and bottom. So this becomes 3 root 2 times 3 over root 3 times root 3 is 3. Of course, these cancel out, and so this is now root 6. So I'll say root 6. Box the answer. Make sure it's nice and clear. Okay. Next one, I've got 2 minus root 6 in the bottom. So I'm not going to multiply by root 6. I'm going to multiply by the conjugate, which is 2 plus root 6 over 2 plus root 6. And then you got to distribute that. So on the top, that's 4 times 2, which is 8, plus 4 times root 6. That's just 4 root 6 over... now, you could distribute this and be annoying and say that it's 2 times 2 plus 2 root 6 minus 2 root 6. But these middle terms are always going to cancel. That's the point of the conjugate. So I'm just going to use difference of squares identity. It's 2 squared minus root 6 squared. So that's just 8 over 4 plus root 6. 8 plus 4 root 6. That's 4 minus 6. So it's really 8 plus 4 root 6 over negative 2, which equals negative 4 minus 2 root 6. So that's my answer. Negative 4 minus 2 root 6. Done. I think a common mistake here is some people will only divide the 8 and negative 2 and they'll leave the 4 root 6 alone. No, the 4 root 6 gets affected by a 2. The other mistake is people will apply the division of 2 to the 8, to the 4, and to the 6, meaning some people may have written negative 4 minus 2 root 3. That's not true. I can't do that unless I'm dividing by a root. Yeah, that doesn't work. All right. Next one. Oh, easy. Just multiply by the denominator on top and bottom. So this becomes y cubed root xy over xy. Of course, one of those y's is going to cancel, giving me y squared root xy over x. And that's it. I can't really go any further than that. Y squared root xy over x. Okay? That's fully simplified. Okay. Number 7. Determine the inverse of the following functions. Okay, so remember the steps for this. That should be in your notes. But the step 1 is to change f of x to y. Step 2 is to swap x and y. Step 3 is to solve for y. So I will start by subtracting 1. And then I'll square both sides. Then I'll add the 3. And then I'll divide by 2. Which means x minus 1 squared plus 3 all over 2 equals y. So I finalize my answer as f inverse of x equals, I'll just keep it in one numerator, one denominator. X to the minus 1 squared plus 3 over 2. Or you could write it as, right, hold on, let me box it. Nice little box. I could write it, say, or 1/2 x minus 1 squared plus 3/2. That might be a little bit more proper vertex form for our quadratic right there. But that's fine. I don't really care. I just care that you found the inverse, okay? That's good enough. All right, step 1, write g of x as y. And then let's swap x and y. Negative cube root of 2 minus x over 5. Okay, so first, deal with that negative. Put the negative on the other, so multiply both sides by -1. So that way negative x equals cube root of 2 minus x over 5. Now we'll cube both sides. So this will be negative x cubed equals 2 minus x over 5. And then move this over like so. Oop. Oh, I guess I switched for my colors, huh? Whoops. Oh, well. Maybe we'll just keep up that. Maybe we'll just alternate every problem. So if you cube negative x, that's negative x times itself, like that. That's 3 negatives, which is still negative. So this will become negative x cubed equals, oh, those are supposed to be y's now. Those are all y's. Sorry. Y. 2 minus y over 5. Now we'll multiply both sides by 5. 2 minus y. We'll subtract the 2, so it'll be negative 5x cubed minus 2 equals negative y. Divide by a negative, so it becomes 5x cubed plus 2 equals y. Therefore, f inverse of x equals 5x cubed plus 2. Ah, that's really pretty. That's a nice inverse. How nice. How lovely. Cool. Yeah. Yeah, that's good. That's good. There's a double negative in there. Okay. Moving on to 8. Solve each equation. And I want you to notice, remember that we are still in the basics section. Okay? We are still in the basics section. That doesn't mean that this stuff's easy. All right? I didn't call part 1 the easy problems. I never said that. Sometimes the basics are hard. But these are the basics. These are the fundamentals we gotta know. Okay? All right, let's solve each equation and check for extraneous. And check for extraneous means we take our answer, plug it back in, and make sure it's true. Okay, so let's isolate our radical here by subtracting 1 from both sides. Negative root 3/4 x equals 2 minus 1 is 1. Let's move that negative on the other side by multiplying by a negative or dividing by a negative, who cares, equals -1. Then we'll square both sides, so it's now 3/4 x equals -1 squared, which equals 1. Here, we'll do 3/4 x equals +1. And we'll multiply by the reciprocal of the fraction here. We'll multiply by 4/3 on both sides. That way we get x equals 1 times 4/3, which is 4/3. Okay, so does x equal 4/3? We want to check for extraneous, right? Oh, man, I don't want a parallelogram, please. I would like a rectangle. Thank you. So let's check for extraneous. I'll do that real quick in yellow. Check. 1 minus square root 3/4 times 4/3 is my placement for x. Does that equal 2 question mark? Well, that's 1 minus root 1, which equals 2, so that's 1 minus 1. Oh. Oh. Hey. You know what? I thought it was, when I made this, I thought it worked out. But it doesn't? No? I want to verify with Desmos real quick. 1 minus root 3/4. I'm not questioning my logic here. I just, when I constructed this problem, I thought it would have an answer. And I say that y equals 2. Look at that. The square root curve never touches 2. Wow, that's beautiful. So actually, I was wrong to just box that. I was so confident. No, that's not true. I say no. Let's erase our pretty box. So my answer is actually no solutions. Okay. Careful there. See? Look at that. Mr. Spake was so confident that answer was true, he just went ahead and boxed it. And he only did the check because he thought, oh, that would be fun to do, I guess. It was important I did the check, isn't it? It is important that I checked that this equation actually have a solution. Also, hey, psst. Should have been a red flag here. This says 1 minus some number equals 2. And whenever you take the square root of a number, you'll never get a negative, which means that's never going to be true. I would need that result to be -1, and that's not going to happen. All right. Let's do the next one. So to do this one, we raise both sides to the reciprocal powers. So if it's to the 3/2, I'm going to raise that to the 2/3. And I'll do that on both sides. Some students have been describing this as multiplying by the reciprocal. Okay, careful with your language there. True, the idea is that you're looking at the exponent and multiplying the exponent by its reciprocal. But what are you doing to the equation? You are not multiplying by the reciprocal, you're raising to the reciprocal power. So raise to the reciprocal power. Okay, that's what you're doing. So this is now 2x plus 10 to the first power equals, well, I guess that is cube root of 4 squared. Now, we could simplify that real quick, because 4 squared is 16, and I know that there's an 8 in there. So see, look, this is cube root of 4 squared is 16, and that's cube root of 8 times 2, which equals which equals 2 times cube root 2. Yeah? May as well simplify that while we're here. And so I'll say 2x plus 10 equals that, which means 2x equals 2 cube root 2 minus 10. And then I will divide both sides by 2, which yields my solution. X equals 2 over 2 is 1, so that's cube root of 2 minus 10 over 2, which is 5. And now you have to test this answer. Is it true? I don't know. I am not going to do the math by hand. I absolutely can, but this one, I would say check with a calculator. Check with calc. Just take your cube root of 2 minus x and store that for x and then verify it, okay? So if you're not sure, actually, this might be a good time to do that. Look, I'll do, what? Don't track me. Stop. Just stop taking my information. You don't need to know where I am at all times. Thank you. So what I say, cube root, so I go to math, I make the cube root of 2, and we are going to do minus 5, right? Is that what our answer was? Yeah. Okay, and I'm going to store that for x. Enter. Okay, and now I believe the equation was 2x plus 10 to the power of 3 halves. Oops. Delete. 3 over 2, like so. Is that right? Yes. And I want the result to be equal to 4, so enter. Hey, buddy, look at that. It's 4. So, done. It is true. Therefore, x equals cube root of 2 minus 5. Nice. That's so beautiful. You know what? I like the therefore, so I'm going to go put it over here too. Therefore, no solutions. All right. And that's the basics. Yeah. There it is. Hopefully, that covers like 70% of what's going to be on the test. Right there. Okay? And I guess I'll keep going. No. Do I make another video? I'll just keep going. Whatever. If I need to stop for my sanity, I can. But I'm fine. I'm doing fine. I'm having fun. It's just my friend wants to get on and play games or watch a movie. My girlfriend and I, we want to go get food. We don't know whether we want to get Pluckers or Wingstop. So I'm just kind of, I'm like, I want to hurry up this video so I can go have fun and enjoy my Sunday night. Oh, man, time passes. Okay, number 9, rewrite the function. So we've done this in class, and I've explained this in class and showed you, but hopefully, if you haven't got it by now, here it is, okay? Here it is. The idea is you want to look and see, is there anything I can factor out of my expression that I can take the square root of? Because if you can take the square root of it, then do that, right? The idea, right, the basic example might be 4x minus, 4. If you can pull the 4 out, so it's x minus 1, then that's square root of 4 times square root of x minus 1 by the property of multiplying these things. So that's 2 root x minus 1. That's the basic idea. So, and I'm looking at this one, right? F of x equals negative 1/3 root 36x plus 108 plus 8. Okay? Well, I know that 36 is a perfect square. Yeah? So, this is negative 1/3 root 36x plus, and is 180 divisible by 36? Yes. 36 times 10 is 360. Half of 360 is 180, so that's a 5. 36 times 5 is 180. Which means you can separate this now as root 36 times root x plus 5 plus 8. Of course, the square root of 36, that's 6. I'm just writing these guys. And now negative 1/3 times 6 is negative 2. And then I've got my root x plus 5 plus 8, like so. Okay? And that is as simplified as it gets. I say negative 2 root x plus 5 plus 8. Done. Okay, and now what I have to do is plot my graph with at least 3 points and connect them smoothly such that it looks like the parent function I'm trying to graph. Now, and I'm going to write this in yellow so that it's nice. Let's find the endpoint of our square root function using parent function transformations. Okay, I'm writing that down so it's on the notes. What I mean by that is your original endpoints is at 0, 0. So the only thing that's going to affect that endpoint is shifting left or right and up and down. Now, a plus 5 is a shift left 5. See, when I write -2 root x plus 5 plus 8, this is doing a few things. The -2 is a vertical stretch and a vertical reflection. The plus 5 is left 5, and the plus 8 is up 8. Now, that endpoint is just going to shift where left 5, up 8. So I'll go 1, 2, 3, 4, 5, and then up here at 8, boom. That's my endpoint. So one of the points I have is -5, comma 8. Okay. Also, if you know your function transformations, you know that because it's a vertical reflection, it's going to look like this. So don't bother testing points to the left of -5. That's not going to work. You're going to take square roots of negatives, and you don't want that. So let's try x to the -4. Maybe I'll test this in blue. Let's say x equals -4. Then this is -2 root -4 plus 5 plus 8. That's -2 root 1 plus 8, which is just -2 plus 8, which is 6. So at -4, I have the point at 6. So -4, 6 is right here. Let's test another point. Don't do -3, because if you do x equals -3, look, I'll just write it for you. -2 root -3 plus 5 plus 8. That's -2 root 2. And we don't know the square root of 2, so it's not going to give us a pretty point to graph. So I'm not going to test 3. I ask myself, I've taken the square root of 0. I've taken the square root of 1. The next one I want to take the square root is 4. So what value for x plus 5 is 4? That'd be -1. So this is now like so. -2 times root 4. Well, that's -2 times 2, which is -4 plus 8, which is 4. Okay? So when I put in -1, I get out 4. All right. -1, comma 4. And that's enough. You don't have to keep going. You probably could keep going, though. If you test x equals 4, 4 plus 5 is 9. Root of 9 is 3. That's -2 times 3 is 6. -6 plus 8 is 2. So actually, there is a point right here. At 4, comma 2. And then 16, x would have to be 11, so I don't have enough space for that. Okay, so let's make my square root curve. It's going to look like this. Oh, iPad, I didn't want you to... Okay, I guess it won't be completely smooth. All right. like that. Okay? Isn't that beautiful? Look at that. Look at that graph. Boom. Arrow. Nice, solid arrow. Okay, that's your square root graph. I have 4 points on there, but remember, you just want at least 3. Where's my highlighter? You must provide at least 3. Yeah? Let's do that in yellow. At least 3 points. You can have more than that, though. You're absolutely welcome to have more than 3. Okay, number 10. Let's keep going. All right. I'm going to do a switch to... I'll keep the same color scheme. We'll just do red. So let's factor out some business here. I'd like to factor out the negative. I guess you don't really have to. It's not any better or worse by doing that, but I don't know. I personally prefer factoring out the negative. So negative 16x plus 48, and then plus 1. So I'm going to do factor out negative 16, and this is now x minus, I think 16 times 3 is 48. You see, I'm factoring out 16 because that's a perfect square. Oh, except, hey, uh-oh, cube root of negative 16. Wait a minute. That's not what I want, right? I don't want cube root of negative 16 because I can't take that, right? So, shoot, right? I might say, darn. So, let's try this again. I'll do cube root of negative 16x plus 48 plus 1. Now, instead of factoring out 16, because I'm not doing square root, I'm doing cube root, right? Cube root, not square root. So I can take the cube root of 8, though. So I say cube root of negative 8. And then here I've got 2x minus 6. All right? And then plus 1. Now you can separate this as cube root of negative 8 times cube root of 2x minus 6 plus 1. So that's cube root of negative is negative 2 times cube root 2x minus 6 plus 1. And I'll say I would factor out 2. That way it's negative 2 cube root 2x minus 3 plus 1. The reason for this is it'll tell you where your endpoint is much easier. Negative 2 cube root 2x minus 3 plus 1. Okay? Now look, all of these do their own thing. This, again, is vertical reflection and vertical stretch. I'm analyzing parent function transformations. This 2 here is a horizontal, not stretch, but compression. The minus 3, that's a shift right 3, and the plus 1 is up 1. Okay? So let's plot that point. Just like I said up here, I'm going to lasso this. Lasso, copy. I'm not finding the endpoint, though, because a cube root does not have an endpoint. It has something else. Find the inflection point using parent function transformations. So your inflection point, that's also the thing that's at 0, 0, because your cube root looks like this, right? We're going to shift that right 3 up 1. So it's going to be shifted up here, and that's going to be our place of inflection. So I'm going to erase that. Let's go back to red. So right 3, up 1. Right here. That's my inflection point. So I'll say 3, 1 is inflection point. Now, I have said you would like to have 3 points. And I noticed that sometimes on the homework or quiz, actually I think just on the homework, some students got 2 points over here, and then they graphed it like this, but that middle point's not the inflection point. So here's Mr. Spake's recommendation. Graph 1 point to the right of the inflection point, graph 1 point to the left of the inflection point. This will give you the most accurate graph. Now, I did say only 3 points, so look, if you find 2 points on the right and you just want to use those 3 points, that's fair game. I don't mind that. Just know that your curvature has to be correct, and that change in the concavity, the change in the curve of your cube root or cubic needs to be where the inflection point is. So let's start plugging in numbers. I've got, well, what do I even want to test? What can I take the cube root of? Let's take a look at this guy. We got to think about this. I don't want the lasso tool. Whale. We've tried x is 3, which makes it goes to 0. I don't want to do 4. That is a silly idea, because 4 minus 3 is 1. 2 times 1 is 2. Can't take the cube root of 2. I would like to take the cube root of 1, but I will only get that if I plug in something fractional for x, which I can't do. So let's try cube root of 8. So I need a 2 times 4. So what number minus 3 is 4? That looks like that would be 7. Okay? Do you see how I've logicked that out? The goal is cube root of 8. Yeah? I want the cube root of 8, but I'm looking at the cube root of 2 times x minus 3, which means I want x minus 3 to equal 4, which means I want x equals 7. That way I get a nice, pretty number I can take the cube root of. That was my thinking and logic behind this. So let's test x equals 7. Let's test x equals 7. That's negative 2 cube root of 2 times 7 minus 3 plus 1. That's negative 2 cube root of 2 times 4, which is 8, plus 1. So that's equal to negative 2 times 2 plus 1. That's negative 4 plus 1, which is negative 3. So my result is 7, negative 3. 7, negative 3. Yes. Okay. Now, hey, psst. By the way, this is a hint. This is a trick. Cubics and cube roots have a type of symmetry. They have diagonal symmetry, which means if I flip this diagonally, it's over there. So look, I found this point. It's 1, 2, 3, 4 over to the right. So to find its symmetrical point, I'll go 1, 2, 3, 4 to the left. And then this was 1, 2, 3, 4 down, which means I go 1, 2, 3, 4 to the right. Or up, I mean. So actually, I should have a point here at negative 1, 5. But I'm going to do the math to make sure that that is actually true. So let's do it. X equal negative 1. Negative 2 cube root of 2 times negative 1 minus 3 plus 1. That's negative 2 cube root 2 times negative 4, which of course is cube root of negative 8, which is negative 2 times negative 2, which is 4 plus 1, which is 5. Look at that. And so the symmetry holds, yeah, by doing that. Okay, now all the matter is actually making the root curve look correct. Now here's what I'm going to do. I'm going to sketch it with my little laser pointer here. It's a cube root, right? Which means it needs to look like this. Or if it's flipped, it needs to look like this. You do not want it to look like a cubic. You see, it could be very easy to say, ooh, right? But that would be x cubed. I need something more along the lines of, oh, well, that was horrendous. We want to connect it like that. Oh, I wish that was my actual line that I just drew. Oops. Let's see if I can do that again without messing up. Oh, wrong. Try that again. Boom. Oh, look at that. Now that's a beauty right there. That's a beautiful cube root right there, at least as far as I can do on the iPad. So, boom. I got my curvature there. You want to make sure that curvature is nice. I won't be too picky, but I will be a little picky when I grade these tests because your curvature needs to look like a cube root, okay? If you mess up a little bit with the concavity of up and down, well, I don't know. Most I would take off is like a point, 1 point for that. Okay, let's move on and going forth. Let's graph these functions, okay? Yeah, and this is just practice graphing, just getting right into it. So this is just plugging in points. That's all this is. And then graphing the inverse, which you just switch your x and y values. So, okay, look, let's make our table x and y, and let's test some stuff. First good choice would be negative 4. Okay? We want to test negative 4 because that's what's going to make that go to 0. Because square root of 2 plus negative 4 over 2, that's square root of 0. And 3 times root 0 is 0, so it's negative 5. And that's where my endpoint is, negative 4, negative 5. And maybe I'll write that down. Endpoint of square root can be found by finding the x value that guarantees root 0. Okay? If you can make the radical, if you can make the radicand equal to 0, that x value will be your x coordinate of the endpoint. The reason for that is you can't have square root of negative. If you do, you get imaginary numbers. And I can't graph imaginary numbers. So 0 is the last real point you're going to be able to graph, whether that's going left or right, okay? Okay, so let's test some more stuff. Remember, what you're really looking for is square root of 0, square root of 1, square root of 4, square root of 9. That's what you're looking for. So negative 4 gets us square root of 0. That's by plugging in negative 4. I can get 1 by plugging in x equals negative 2. You see, because 2 plus negative 2 over 2 is 1. So, and I know I'm just verbalizing that and not writing it, but I don't really want to write it. Square root of 1 is 1, times 3 is 3, plus 5 is negative 2. So negative 2 is one of my points. Then if I want the square root of 4, I'm going to need a 2 plus 2, which means I'm going to need a 4 over 2. So a positive 4 is going to work here. So square root of 4 is 2, 6, negative, boom, 1. 4, comma 1. Can I graph one more? Can I get away with it? I need a 7. I would need 14 to accomplish that. You see, because what I need 2 plus x over 2 to equal 9. So what I'm doing in my head is I'm subtracting 2 from both sides and getting x over 2 equals 7. And then I'm multiplying this so it's by 2, so it's x equals 14. And I can't graph that because my grid doesn't go that far. So I'll just put a little x next to this. And that's 3 points, which is good enough for me. So boom. There's your square root curve. Now to graph the inverse, we're just going to flip all those points. So negative 5, negative 4, negative 2, that's the same, and 1, 4. So negative 5, negative 4, negative 2, and 1, 4. And negative 5, 4 is your inverse, is your endpoint, so it's going to look like that. Ugh. You know, I'm gonna zoom in, and I'm gonna make my arrow, and I'm gonna come down like this. Okay? Oh, I don't like it. I'm picky. I'm sorry. I'm picky with myself. I guess that's okay. I wish it could be nice and smooth. But let me see if the iPad will do it. I'm so sorry. I'm so sorry for taking up more of your time. But if you hate it, you can just skip forward. Stupid, bendy nonsense. How about this? Okay. There we go. There, that's good enough, I think. Okay. Boop. Boom. There's your square root. Okay. I like it. Okay, let's keep going. Graph the function g of x equals cube root, blah, blah, blah. Look, I want cube root of 0. I want cube root of negative 1. I want cube root of 1. Maybe I want cube root of negative 8. Maybe I want cube root of 8. I don't think I want to go up to 27, though. So let's think, what could I do to get these things? Well, if x is 0, that's going to check out, right? Let's make my table, x and y. If x is 0, negative 0 over 3 is 0, cube root of 0 is 0, minus 2 is negative 2. So that's my inflection point, 0, negative 2. So what could I do to make this negative 1? I could plug in positive 3. Positive 3 over 3, that's negative 1. Cube root of negative 1 is negative 1 minus 2 is negative 3. So, boom. Okay. Now, if I put in negative 3, I'll get that positive 1 out. So put in negative 3. And that result, I believe, is going to be negative 1. Yep, negative 1. So negative 3. Wait. Hold on. Wait. I'm sorry. I didn't plug in negative 1. I plugged in. Oh, don't do that. I plugged in 3. Silly. What are you doing, Mr. Spake? You silly dog. 3, negative 3. And then negative 3, negative 1. Okay, that's better. Whew. To get negative 8, I would need 24. And that's not going to be graphable. And neither is negative 24. So those are my 3 points. That's good enough. So let's try and get this curvature right here. It needs to... You see, it needs to curve up this way, but it needs to curve down this way. And there you go. By the way, do you see how I broke that up? That's probably the cleanest way to graph cube roots. Curve up, curve down. Okay? That's probably the cleanest way to do it, to make sure that that curvature here follows. Because when you try to do it by hand sideways like this, you just don't get something that looks very symmetrical. So that's maybe my recommendation right there. Okay, so let's invert these points. Let's swap x and y. So it's negative 2, 0. Right here. That's the new inflection point. And then negative 3, 3. That's negative 3, 3. And then negative 1, negative 3, negative 1, negative 3 down here. Okay? And again, like I just said, let's split that up. So just do that first leg like this, and then we'll do the second leg like that. Okay? Boom. And that's a decent cube root curve. Or sorry, that's a decent cubic. Like so. Nice. Good. Oh man, we're almost through part 2. How long is this video? Sheesh. Okay, number 13. Solve the following equations. Hint, you will need to factor a quadratic. But I didn't even talk about what part 2's title was, did I? Part 2 is applying our knowledge from previous units. Our knowledge being parent function transformations and factoring. Those are the main things. So let's do it. I need to, it's always the general rule of thumb. Good idea to isolate radical, then use reciprocal powers to get rid of the radical. And of course, right, if it's square root, you're going to square that because that's x to the half, and you're going to use the reciprocal power of 2. Okay? So looking at number 1 here, let's do my work in blue. I'll subtract x from both sides, so it's root x equals 6 minus x. Then I'll square both sides, so it's 6 minus x squared. And so then this will be x equals, let's expand that. When you expand it, you'll get x squared minus 12x plus 36. I'm not going to explain how to do that because, like I said, you should know this. You should be able to get that by now. 0 equals x squared minus 13x plus 36. And if I factor that, that's going to be x minus 9, x minus 4. Is that right? Yes, it is, which means my solutions are 9 and 4. So let's check, because you have to check for extraneous. Square root of 9 plus 9 equals 6, question mark. Well, that's 3 plus 9, which equals 12. So no, that is not true. So 9 does not work. Let's try 4. Square root of 4 plus 4. Does that equal 6? Well, that's 2 plus 4, which is 6. Yes. Therefore, x equals, and I'll use a set here, 4. I don't think I did that earlier, but that's okay. Therefore, x equals 4. Okay? That's actually a pretty basic problem. You isolate the radical, and then you square both sides. And then it's just a quadratic that you factor and then check for extraneous. Done. So is there anything else I want to say on this? I don't think so. Okay, letter B. Let's isolate our radical again. X plus 9 equals 2x minus 10. We will now square both sides. And if you're wondering why I'm not... Look, I could write square root of this squared. But what's going to happen is that that's just going to be x plus 9. Okay? So I don't bother writing that part in my work. You can. I don't care. Write it, don't write it. I'll follow your work. It'll be fine. Okay, let's expand that nonsense on the right. Blech. X plus 9. Sorry, my eye is starting to water. 2x times 2x is 4x squared. Minus 20x, double that, it's 40x. And then plus 100. Let's move all this junk over. 0 equals 4x squared. Minus 41x? Ew. Really? And then plus 91? What? 91? Ugh. Ew. Gross. Ugh. I thought this was going to be easily factorable, but I guess not. What do I want to do? I'm scratching my eye. I'm sorry. It's all watery. Fine. I guess we'll do factor by grouping. This one's kind of gross. 4 times 91 is 364. Uh-huh. And then this is negative 41. Sheesh. Oh, boy. Oh, boy. 364. I think I can divide that by 4. Get 91. Nope. How about 8? 364 divided by 8 would be 43. So 8 and 43. 43 is prime, isn't it? Ooh. How doth little this factor? Maybe it's not factorable. That's what my gut says. Is it factorable? Mr. Spake's gut says no. So, tried and true, everybody. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There it is. Okay, well, I'm not doing that by hand. Calculator time. By the way, this is the part of the test where I let you use the calculator, so thank goodness. What is that? 41 squared. 41 squared minus 4 times 4 times... What was it? 91? Was it really 91? Who came up with this problem? Me. I did. Was it? Come on. 91. 225. Oh, wait a minute. 225. I recognize that. That's 15. Oh, I guess we didn't have to use quadratic formula. X equals 41 plus or minus root 225 over 2 times 8. So 8. So that's 41 plus or minus 15 over 8. So 41 plus 15 tells me x equals 56. And minus 15, brain fart, 26? Is 26 plus 15 that 26 plus 15? Okay. Good. So now we just got to test this. Huh. All right. Let's check. Oh, shoot. That stuff's divided by 8, isn't it? That stuff is divided by 8. 56 over 8, 26 over 8. Now, 56 over 8, that's just 7, ain't it? And 26 over 8, that's 13 over 4. So we got to check for extraneous. Check. I can do 7 by hand. That's no problem. Root 7 plus 9 plus 10 equals 2 times 7, question mark. That's root 16 plus 10 equals 14. And root of 16 is 4 plus 10 equals 14. Yes. So 7 works. Does 13/4 work? Do I want to do that by hand? No. So I'm going to do calculator. Okay? Use calc for 13/4. Let's go to calculator. Let's clear this. 13 over 4, store that for x. Boom. And it's square root of x plus 9 plus 10. Okay. Square root of x plus 9 plus 10. I get 13.5. And 2x, which is the right side of the equation, is 6.5. So I don't think that's true. False. Okay, therefore, x just equals 7. Terrible box. Terrible, terrible, terrible. Oh, stop. By the way, I want to show you one more thing. I cannot get this box. Hello, Mr. Trapezoid. Stop that. And be a nice, pretty rectangle for me. Conform to my expectations. Okay. You can check this very quickly with Desmos. Root x plus 9 plus 10. Okay. So, root x plus 9 plus 10. And then the other line is 2x. And there is one point of intersection at 7. There is no other point of intersection, meaning there's only that one solution. Okay? Means that other one was extraneous. It was not true. It was false. And there you go. Oh, but do notice, look, so if I type in x plus 9, okay, so here, watch this. So if I do 2x squared, 2x minus 10, and I square that, what do you do? What? Stop. Square it. Okay? And then I do x plus 9, not in the square root. I do get 2 points of intersection. The first being 7, the other being 3.25. And what is 2.25? It's 13 over 4. So you see, when I square that and I compare the graphs of the parabola and the line, there's 2 points of intersection, which means there's 2 solutions. But when I actually check, that 1 point does not work. So we're good on that. Okay. Oh, man. Part 3. Have you mastered the material? Okay. I'm stopping the video here for now. This will be the end of part 1. I'm going to do the mastery part later, probably tomorrow. I do have the energy to do it right now, but I think my girlfriend's hungry. So we need to order food and go do that. And And I also don't want to lose my whole Sunday night to doing this. Also, The Last of Us TV show is coming out tonight. Hooray. Maybe that'll be good. Probably nowhere near as good as the game, but that's okay. It may still be entertaining. Okay. End of video. Hope that was helpful. See you in part 2 later.